Now that we understand how to find curl of F, we're going to come back to Stokes' theorem. And for Stokes' theorem, we are requiring our surface S to be an oriented, smooth surface bounded by a simple, closed, smooth boundary curve C with a positive counterclockwise orientation. So let's visualize this. Here's my coordinate axes. So I'm going to envision my curve being the base of this hemisphere. So we've got a hemisphere here. And so we've got along the base of that curve, right, we need to make sure that we are traveling in a counterclockwise direction. So there's a smooth boundary curve. It's a nice smooth circle. We've got a counterclockwise orientation. And my surface is the top of this hemisphere, right? All of that represents my surface. Now it just looks like a beehive. But the top of this is my surface. So I've got a surface. I have a curve C. And the main thing that we want to talk about here is that this is oriented. It's oriented, so it's facing up. So again, here this is oriented to face up, but again, that depends on C. So you want to think about if you were a little person traveling around this loop, you would want the surface to be on your left, right? So if you drew a little guy right in here he is. Here's my little guy. He's walking around, he's facing the front of the loop. The surface, if he's facing this way, traveling this way, the surface is on his left. So the orientation depends on the direction of that path. So oriented up in this counterclockwise direction is what makes it simple, right? If this was oriented down, we would maybe be traveling in a clockwise direction in order to keep that path on our left side. So that helps you kind of get an idea of what we mean by oriented. So now that we understand our conditions, let's talk about Stokes' theorem. So suppose that this surface is piecewise, smooth, and oriented, right? And these are all conditions that must be met. And it has a piecewise smooth boundary curve. So this curve needs to be smooth. Then we have the vector field with components, and those components have to have continuous first partial derivatives on that region S. Then the circulation of the vector field around the curve in the direction counterclockwise with respect to the surface's unit normal vector n is going to equal the integral of the curl vector field over S. So again, with that notation, thinking about this line integral now as a surface integral. And when we talk about that normal vector, it's normal to the surface. And I think this graphic from the book kind of gives you a better idea. We've got this counterclockwise path around the curve. The surface is on the inside or the left if we were traveling. And then we've got this n. That is a normal unit vector, which means it is perpendicular to the surface, and whatever is traveling around that is also moving in that counterclockwise direction. So I didn't want to really get into the derivation of this. There is more in your text. I just kind of want you to see how to evaluate these integrals. And when you get to your physics class and you're working with your physics instructor, they'll give you more meaning as to what these integrals mean, right? They'll give you some more background behind them. But regardless, let's do an integral. We're going to use the surface integral in Stokes' theorem to calculate the circulation of a field around a curve. In this example, as I've already stated, we're going to use the surface integral from Stokes' theorem to calculate the circulation of the field F, a vector field, around the curve C in the counterclockwise direction. So our vector field is 2yi plus 3xj minus z squared k. And the curve, our path, is x squared plus y squared equals 9. So it's a circle of radius 3 centered at the origin in the xy plane. And again, from above, we're traveling in a counterclockwise path. So in order for us to use Stokes' theorem, we first need to calculate the curl. So the curl of f, and we did this in the previous example, is del cross f. Or rather, we're going to have I, j, k. We've got partial with respect to x, partial with respect to y, and partial with respect to z. And then each of the components from f, we've got 2y, 3x, and negative z squared. So this is going to equal I times partial with respect to y of negative z squared minus partial with respect to z of 3x. And then we'll have minus j. It's always that minus second. So minus j partial with respect to x of negative z squared minus partial with respect to z of 2y, and then plus k, which is partial with respect to x of 3x minus partial with respect to y of 2y. So simplifying each of those, I've got I, end it with 0 minus 0, so that's 0y, minus j, I've got 0 minus 0, plus k. Calculating all these partials, I end up with 3 minus 2. So this ends up giving me that this is equal to 1k. Or we can say that the curl of f equals k. And then this lets me know that my unit normal vector is also going to equal that k unit vector. So when I go for my second part, I need to calculate the curl of f dotted with n. That is 0, 0, 1. That vector represents the curl of f. Dotted with 0, 0, 1. This vector represents n or k. And that gives us a value of 1. The third piece that we would need here is we need our surface area differential. And in this case, d sigma, since we're just dealing with x and y variables, is going to be dx dy. So the last piece here is we will set this up. So my integral by Stokes' theorem, that is the path integral along the curve C of f dot dr, is by Stokes' theorem equal to the surface integral over the surface S of the curl of f, or del cross f, dotted with n. And we just calculated that. All of that is equal to 1, and then we have d sigma. So in this case, this is going to be the double integral over that region of just dx dy. So setting that up, since it's a circle of radius 3, we've got the double integral from 0 to 3, 0 to 3 of dx dy, and all this is the area of a circle with radius 3, which is pi r squared, pi times 3 squared, or 9 pi. So this value represents the circulation of the field around the curve in the counterclockwise direction across that surface. So that's how we use Stokes' theorem to evaluate an integral. And, email me if you have any questions. We're going to do one more example in the next video. Stay tuned.